My name is Kevin Lynch. I serve as director of the Center for Robotics and Biosystems at Northwestern University and as research director for the HAND ERC. The HAND ERC is a consortium of universities led by Northwestern, Texas A&M, Carnegie Mellon, MIT, and Florida A&M, companies, government research labs, and nonprofits, all dedicated to the mission of revolutionizing robotic dexterity and making it broadly accessible. In addition to our research and development of application test beds, one function of the HAND ERC is to convene the dexterity community to discuss emerging technologies and key research challenges and applications. For those of you who will be attending ICRA in Atlanta in a week and a half, the HAND ERC will be co-hosting a workshop on Monday, May 19th. The title of the workshop is Handy Moves, Dexterity in Multi-Fingered Hands, and it features leading researchers and companies working in robot dexterity. But today I'm excited to introduce our panel on dexterity for humanoids. There has been tremendous recent energy and investment in humanoids, and I would say that dexterous manipulation is perhaps the most important and hardest challenge for humanoids. The hands are where advanced AI turns into useful physical work on the world. Today, we're fortunate to be joined by thought leaders in humanoids and dexterity from Boston Dynamics, Apptronik, and Sanctuary AI, who will share their insight on challenges and opportunities in dexterity. If you have questions, please submit them through the Q&A function, and they will take your questions later in the webinar. Now it is my pleasure to introduce our panel moderator, Brenna Argall. Brenna is a professor of computer science, mechanical engineering, and medicine at Northwestern, and she runs a human augmentation robotics lab at the Shirley Ryan Ability Lab in Chicago. She's also the lead of the HAND ERC's Intelligent Dexterity Thrust, addressing topics such as machine learning, simulation, and control for robot dexterity. Brenna, I'll turn it over to you.
Thank you, Kevin. It is my pleasure to introduce our panelists. Jeremy Fishel is principal scientist at Sanctuary AI, where he leads efforts to enhance the dexterity of Phoenix, its general purpose humanoid robot. His PhD research at USC contributed to the invention of the BioTac sensor and advancements in robotic touch, later commercialized by Sentis, which he co-founded. He went on to form Tangible Research to develop the tactile telerobot and other technologies for high-performance teleoperation. Tangible was acquired by Sanctuary AI in 2023. Next, we have Roberto Rodriguez, who is the Director of Robot Behavior for the Atlas Humanoid Project at Boston Dynamics. There, he leads teams working on controls, perception, planning, and machine learning behavior to bring the Atlas humanoid to scale. His passion is to work at the intersection of hardware and software to build robots with physical intelligence. Before joining Boston Dynamics, Alberto was faculty in the mechanical engineering department at MIT, where he led the M-Cube lab. And finally, we have Louis Sentis, is a professor of aerospace engineering at UT Austin and is the chair of UT Austin's Good Systems. He earned his PhD in electrical engineering from Stanford University and was a Lucaxia Fellow. At UT, he leads the Human-Centered Robotics Laboratory, focusing on the design of humanoid robots, human factors, and space robotics. He is also a co-founder and innovation advisor for Apptronik Systems, a company that is building humanoid robots for industry and home applications. So thank you all so much for being here with us. Jeremy, let's start with you. Your work on tactile sensing and dexterous teleoperation with the tactile telerobot has been enormously influential. Tell us what you're working on at Sanctuary to take dexterous manipulation to the next level.
Thank you. Let me share a few slides here. First off, thanks for hosting this and having us be a part of this. Really excited about this workshop and what you all are doing and to share our work on this. Can you see my slides or videos?
We can.
Okay. So at Sanctuary, we've been continuing a lot of that thread, driving durable tactile sensors and really studying the relationship between system capabilities and how those systems perform and advancing dexterity in those directions. So I have a few videos to share. This is our hand. This is our third generation hand. Very anthropomorphic design, very human-like kinematics, and has the right kind of power density that's similar to the human hand. Very important for in-hand manipulation, as we're demonstrating here, that some of our engineers have worked on. And it can do a lot of the things that the human hand can do. So this has been a critical tool for us to really study this relationship between which of these features and degrees of freedoms and speeds and strength actually relate to performing tasks that humans do with their hands, which is really a big philosophy of our company, is we want to be able to do the kinds of work that people can do with their hands as well. So lots of great stuff that we can share about that. One of the ones that I actually think is very exciting work that we've done lately, and I'm kind of glad that I get to talk over this video, is this one that we've demonstrated with this in-hand manipulation type task. So we train this in simulation, and we're doing this rotation. And we do this with actually 500 grams of weight. And it doesn't sound like a lot. I remember seeing this the first time and saying, well, that's just 500 grams. That's not too difficult. But if you have access to weights, I would encourage you to pick up a 500-gram weight and try to do this task. And it's actually incredibly difficult, and really proud of this performance. I can barely do it with 1 kilogram of weight, and at 2 kilograms, it's virtually impossible. So we're really focusing on not only how can we be dexterous, but how do we have the power of the human hand? And we'll talk more about that later, but there's really a ton of conflicts in having these, many degrees of freedom and delicate manipulation and the power, which is something the human hand does an amazing job of. Another thing, and given my background, that we've focused on a lot is tactile sensing. So I made the BioTac at Sentis, which is a very biomimetic sensor. Most of the group's probably seen the green fingertip on various robot systems. And while that system is very capable and can do a lot of things and sense the force, vibrations, and temperatures that human skin can detect, it wasn't very durable. So recognizing that there's been a number of amazing sensors developed, but they haven't been commercialized or industrialized in any significant capacity. We've really focused on the durability and the compliance of these systems while still maintaining that delicacy. So you can see we're able to delicately touch a domino, not knock it over. Another task that's very difficult to do if you close your eyes and try to touch a domino and not knock it over. And we have that sensitivity that allows responsiveness too. This is one of our prototype fingers that's going to come out in a future generation hand. We've got lots of great videos on touch. Let me kind of let some stuff play in the background. So as I mentioned earlier, our focus really has been on this durability and the compliance and the sensitivity. Touch is a very, very critical sense for being able to react to what we're interacting with. So I've always thought of vision as a planning sense, like you see everything in your environment, you decide what you want to do with it, but touch is for adapting to those uncertainties. Like, is the object slipping? Do I need to change my grip? Can I confirm my grip and move on to the next thing? Or how is in-hand manipulation proceeding? So really what we're seeing is touch is very critical for speeding things up. If you don't have this tactile sense, you kind of make a plan. If something goes wrong, you have to stop and make a new plan. Whereas with a sense of touch, you could react and adapt on the fly the way people do. So really our focus at Sanctuary is there's this tremendous range that we see in human hands between being delicate and being able to do these small things to powerful, like the high grasp force that we can attain with our hand. And trying to get that in one package is an incredibly difficult challenge. And that's been our focus, though, is we want to be able to have the delicate tactile sensing, react to small events, yet have a lot of power behind it too. And we'll talk more a bit about that, but we've got our hydraulic actuation that gives our high degree of freedom hands the power that gets much closer to human hands while maintaining that delicacy. And this is my favorite video. And we've been putting tactile sensors on robots and doing teleoperation for almost 6 years now. And we're always seeing this immersive connection with touch. So this is a reaction from one of our engineers flying the robot. And this is the first time we put the sensors on the robot. She's experiencing them for the first time. I hope the audio plays.
Oh, I have touch sensors.
Yeah, are they working right now?
I can't tell. Oh, yes, they are.
That's crazy.
And we see these reactions all the time. It gives this sense of connection. It makes these robots more intuitive to control and manipulate their objects. And it's such a critical sense. So we're really excited to be working with a company that shares our vision here of we need touch, we need power, we need these kinematics to replicate all these amazing things our hands can do.
Thank you, Jeremy. Really fascinating work. Alberto, Boston Dynamics is well known for its videos of tremendously agile and gymnastic robots, but people are perhaps less familiar with its work on manipulation. Could you bring our audience up to speed on what manipulation work you and your team are doing for the Atlas project?
Oh yeah, happy to do it. Thanks for the invitation. It's great to be here, and I have to say, just personally, it's also great to be talking with a different banner on my bag, Boston Dynamics. It's been a nice transition from the work that I was doing a couple of years ago. So let me load up my slides. Sure. All right. So let's see, just a quick one-slider background of Boston Dynamics. There are basically 3 projects that dominate most of what Boston Dynamics does. Spot, which is a product that you can buy, and it's mostly focused on autonomous data collection and asset inspection. So you can think of Spot as a robot that walks around, let's say a factory, it could be other environments. It just records what's happening and it sends warning signals when something looks off, for the most part. Then Stretch is also a product you can buy, and it's a robot that is focused on case handling. Today, it's mostly focused on the deployments we're doing on truck unloading, but sort of extending the range of types of workflows that it can handle. And then there's Atlas, which is what I'm going to discuss a little bit more today, which is our frontier project, research project, looking in the past mostly focused on mobility, and for the last 2-3 years transitioning into mobile manipulation. And before going into more in detail of the type of research that Atlas is doing in Dexterity, I just wanted to have one slider as to why dexterous manipulation, with just one case example of mobile manipulation in manufacturing. If you look in detail, there's 2 large groups of tasks that have not been automated. Those are material handling and assembly, and there's very large variety in the operations that have to be done to fulfill these tasks. Material handling basically has to do with solving the problem of bringing in a gigantic variety of parts that have to be fit into one, let's say a car in this case, and make each part get to at the right time, in the right place in the assembly line. There's just not enough space in the assembly line for all varieties of parts. So there's a very intense logistic problem of making sure that each part gets, the right part gets at the right time in the right spot. And then assembly, similarly, there's a large variety of highly dexterous manipulation tasks that have to be performed with high reliability. And I would say that the number one reason why these tasks have not been automated is not necessarily that they're too complex. Right now, it's incredible the amount of complexity that can be handled with fixed automation. But the problem is that the kind of automation that we're used to requires just too much space and too much engineering capital to deploy it. And in these 2 large group of tasks, there's not a lot of commonality in how these tasks are executed. So it just takes too much effort or too much cost to automate them. So it's not economically worth it. So I would say the number one reason, yes, dexterity, and that's what we're here to talk about. But in parallel to dexterity, I just also wanted to highlight a couple of things that, in my view, they're also very important to be able to solve tasks with variety like this, which have to do more with the cost of deployment, the workflows that we use to enable, develop, and deploy these tasks. If we somehow get to a point where robots are capable of doing more complex tasks, we still have the problem of how do we how do we develop behaviors for each one of these individually. So reaching a degree of behavior generalists and hardware generalists, it's also important to be able to address that limitation. So what is Boston Dynamics doing in this space? Here I just put a video which you might have seen in YouTube. This is Atlas executing one particular workflow for material handling. This is called sequencing. There's these inlet fixtures with different varieties of, this is just one part, this is an engine cover. And this is a fixture where it's inserting it, where each one of these slots gets associated with a car in the assembly line in order. So this workflow is responsible for making sure that the order in which the parts are inserted in the output fixture that will be rolled into the assembly line is exactly the same as the cars that are going to be assembled in order. So we've been building behavior architecture that is capable of executing tasks like this, pick and place behaviors with a certain degree of reliability. But really what I wanted to discuss today is where we're going next, or where we think the next push we're doing to increase the generality of the behaviors that Atlas can do, in particular in the space of dexterity. And for the most part, I would say there's like three main threads that we're pushing on: simulation at scale for reinforcement learning, whole body teleoperation for imitation learning, and grippers with tactile sensing. And I'll just go into just one slide in each one of these. On the gripper side, I would say, just to follow up from Jeremy's presentation, we've taken a slightly different approach. And instead of starting from a humanoid form factor, we've been interested in growing incrementally the degree of dexterity of the gripper as we recognize that we need more dexterity. But at the same time, being able or trying to maintain a certain degree of reliability and strength to support the kinds of tasks that we want Atlas to be able to do with high loads, heavy objects, and with high repetition to do, for example, data collection at scale. Here's one slider on the work we're doing on reinforcement learning. Here's the demonstration of a policy that has been trained in simulation that shows significant degree of generalization to grasping objects. So none of these objects that are showing up in front of Atlas were part of training. It's been trained on hundreds of objects, but none of these were part of the training. And it operates directly from RGB stereo. So there's no prior knowledge of the geometry or the appearance or the mass of these objects. So it all comes directly from either visual or proprioceptive feedback. And one of the things that I am particularly very excited about is that through training these policies at scale, we do see the beginning of emergence of continuous dynamic behaviors that do not separate between pre-grasp or the traditional separation between pre-grasps, grasps, and lifts, and including things like failure detection and retry are things that emerge when you push these at scale. So that's one core thread. And the second one, which we also think that is essential to be able to make progress on dexterity, not just at the hand level, but sort of at the whole body level, is enabling whole body teleoperation that supports data collection across a wide range of bimanual mobile manipulation tasks that include things like crouching to pick up something from the ground or lifting something heavy using both hands at the same time to do regrasps or to lift a heavy object. And here I just show two examples on the left of using a teleoperation system, and on the right, just an example of a policy trained from data collected from the teleoperation system. All right, I think that's my last slide.
Thank you, Alberto, for sharing that really exciting vision for the Atlas platform. Louise, Apptronik has been in the news for its recent success in raising over $400 million, and more broadly, there have been enormous investments in humanoids in recent years. We would love to hear more about your work within this space.
Thank you, Brenna. Thank you, Kevin. Pleasure to be here with esteemed colleagues. Indeed, Apptronik has been a story of success and good timing. And I'm very pleased to be here with other colleagues that are equally, if not more successful. All of us pushing this wonderful market forward. So, if you don't mind, I'll share some slides. And you might know me for having spent the last about 25 years in the area of whole body control of humanoid robots, both as an academic and as original co-founder of Apptronik, where now I am somewhere between business development, fundraiser, and innovation advisor. And the company indeed has started in 2016. It has started selling components. That was our vision at the beginning, but clearly margins were low. And about 4 or 5 years later, we decided that systems, in particular humanoids, as strange as it sounded at the time, was going to be our market. And just a couple of years later, then humanoids has had an investment in the U.S. and Europe, particularly 1x of north of 2 billion, with market caps approaching $50-60 billion. That's without counting China. So it became a thing, and now we have to deliver, and manipulation is at the center of it. But the story of Apptronik starts before Apptronik. It starts with NASA, Johnson Space Center in particular, where whole body manipulation was the most important accomplishment that we could have out of the DRC. What we see here is movies and renderings pre-COVID, about 2017, 2018. They are highly scripted, nonetheless pretty impressive. Using affordances, there's not a whole lot of autonomy except maybe some of the walk, semi-autonomous. But that was already a feat. One important thing to notice here is that out of 33 runs of this task, it was opening a door of a car, finding a bag and zipping it. No, it was not unzipping it. It was putting it in a containment vessel in case they had a bomb, and so on and so forth. We had 33 runs, about 30 minutes each of them. And we were successful in about 57% of them, which is fairly low. The rest of them were failures due to falling and unrecoverable walking situations. And you can go into state estimation drift and so on and so forth. So failure rates, that's again 2017, 2018 were high. I'm gonna argue that they're still high today. And companies like Apptronik and others here are here to respond to these, turning this into a product. And turning this into a product means that we can operate with way more reliability. A lot of the product and engineering is put now on testing, verifying, deploying, robustifying the algorithms of all sorts, whether it's machine learning algorithms or optimization-based algorithms. And I believe that it's going to make things much more successful. Why there's an excitement? Although they have limited manipulation capabilities, even toad manipulation, toads are the kind of things that you see here on the right, on the bottom right side. Those are huge. Box manipulation are huge. And we see a lot of successful unicorn companies, not only in the humanoid side, but also on the industrial arm side, companies like Contoro and Dexterity and Covariant and so on and so forth. Where manipulation really takes real shape is seeing the demographics and seeing that we're going to have about 1 billion people age 80 plus with mobility problems. That makes home really, really appealing. And at home is where we see multi-finger manipulation really thriving. This is a recent video in 60 Minutes with Demis Hassabis and our partnership with Google DeepMind. And you can see that focus and that idea of achieving multi-finger manipulation as a frontier in a humanoid robotics. Going through the time history, and I'm now switching a little bit more to my academic role. This is research we conducted with Yuke Zhu, who's now leading the group project at NVIDIA on using supervised learning, imitation learning, with any sort of interfaces and being able to achieve pretty successful multi-arm, dual-arm manipulation, long horizon or mid-horizon kind of tasks. And that was achieved by a combination of, often supervised learning or reinforcement learning is criticized about the lack of generality. They have robustness, but not generality. And in this case, we create abstractions. They are not necessarily aware of the entire embodiment. So we have on the left side a supervised learning approach, and then on the right side, the kind of a more classical optimization, whole body control approaches. By combining both of them, we achieve robustness and cross-embodiment learning. Here is our extension of using some simple tools that we are seeing now becoming more popular. These are 3D printing, low cost. We actually open source it. There was a collaboration with Boston Dynamics AI Institute, and we gathered data sets in a space, in a representation space that is it can be translated to different embodiments. So you take out the parallel gripper, and now you, with a few demonstrations, you've passed on the skill to other robotic systems. This is our latest work with clients that I cannot mention on exploring fingernails, and we have a high belief that fingernails going to play an important role in tasks like cooking, managing office work, on processing things that are a little bit more exotic, and we're really excited about the combination of soft and hard surfaces for manipulations. You will see more of that fairly soon. That allows us to cover more of the grasping taxonomy and the fine precision on the and manipulation of other type of objects. So we're making a case here for multi-fingers. And perhaps the last couple of slides is that manipulation. We have this home industrial dichotomy, but maybe there's also there's a rehab storyline. Here's a partnership with RoboLegion, one of our favorite companies as well, on grasping human limbs. And in this case, we've been exploring the use of these multi-finger arms. They have quite a bit of force control and tactile control and seals elastic actuation. They have cameras, and they have also speech recognition and speakers as well. So you can talk to it and ground the movements, the dexterous movements into words. Well, safety is another story. We're partnering with another corporation called MITRE for safety. But that's pretty much it. Thank you very much.
Thank you, Luis. Very impressive trajectory. So, Luis, perhaps you can get us kicked off with the first question. What are some near-term or long-term applications for humanoid manipulation that you expect will have groundbreaking impact?
Well, I think I still believe that the killer app, it continues being this millennial problem that from the Chinese to the Turks to the Jewish communities have dreamed of the multi-purpose robot at home, and that is gonna. So sometimes people argue that humanoids is a solution in search of a problem. I want to say that no is a problem in search of a solution. We all want to have the killer app of at-home robots, and we're seeing a clear move by the Metas and the Google deep minds and on that direction. The reason we were seeing the industrial, logistics, retail, humanoid nowadays is because it's easier to make B2B kind of business development, and then penetrating the home markets is a little bit more difficult. There is, Morgan Stanley has a study of, all the whole human labor is several dozens of trillions of dollars, and then pieces of it that humanoids can take are on the order of several trillions of dollars. We're going to be driven by this dream and our ability, particularly in the next 18 months. In 18 months, we're going to know everything, like the future of humankind with with humanoids. I joke around. So we don't have to wait too long to know whether we're going to make it in those applications.
I think, Luis, it's interesting somehow to see it's kind of an inverse. I don't know if you would agree or not, an inverse relationship between the scale of the opportunity, and maybe it's not surprising, the scale of the opportunity and the barriers of entry, right? Like, I agree with you that sort of home is probably the largest potential market that any of these technologies could hope for, but the barriers of entry are huge, especially in terms of safety and the enormous amount of generality that the systems would have to cope with. And manufacturing, it's still extremely complex, but the generalities, I would say, one level below, and logistics or material handling one level below in terms of complexity and barriers of entry, but maybe also potentially the scale of the opportunity. It's not there's not a win-win market, I would say, in terms of winning both on scale and barriers of entry.
If I can respond to that quickly, I think that we've done crazy stuff in the 20th century that it might have sounded like a UFO technology back in the time, right? And we're not, the airplane basically is the Wright brothers, who were bike builders. They had a bike shop basically, right? And they barely flew an airplane at the beginning, right? And then they pitched the business case to the mail industry. And just imagine in 1910, right, pitching the idea that you're going to be flying letters from San Francisco to St. Louis or New York City or whatever, right? And with these barely stable airplanes, right? It sounds bonkers. And sure enough, in 1920, that was the first major application of aircrafts. I think everything here sounds a little bit bonkers, that you're going to have robots at home. And I don't see, people at laundry and the dishwasher and so on. But, we are in a mindset of rich families and so on. But, there is 30% of the families in the US that are single parent. There is people that are having major infestations and mold growth at home. Just keeping the house clean, keeping a plate in front of the child, even for not so well-to-do families. I do see humanoids being penetrating. We need the right business thought leader, that somebody that can push that agenda, the Henry Ford and the Wright brothers of today.
There's another aspect to this I think is important to touch on too, is the general purposeness. So we feel this question a lot of like, why don't we make an application-specific robot to solve a specific problem? And that does tend to be optimal and cheaper. So why would we make this more complex general purpose system? And I think the big picture vision here is the repurposing. So now this one thing can do many tasks, and the repurposing has additional value, and then the scale, right? So maybe these complex, expensive systems can actually get cheaper at the appropriate scale. So that's like a very critical aspect on why this is hot. I encounter a lot of roboticists who are just saying, why are you doing these crazy things when you should be making a specific robot for a specific task? And that's the main point that we try to get across to them, is this repurposing and scale actually shifts the equation into a place where it does make sense.
Thank you, Jeremy. Actually, I'd like to build on that point, if you don't mind. So I'm wondering whether the applications have just been talked about can be achieved using two-jaw or suction grippers. So as you well know, humanoids typically are anthropomorphic. What are the advantages and disadvantages of adopting anthropomorphic hand designs, especially in the context of this universality that you were just talking about?
Yeah, it's a great question, and one that keeps us up at night. I'm sure we've all seen like the amazing things that have been done with the Aloha robot, just two pinchy grippers, just doing phenomenal tasks. And the main thing is speed, right? So I'm fairly convinced that I could do most tasks with a durable pair of chopsticks, but I can't do them quickly. So all of this complexity of the human hand and the tactile sensing, it's about speeding things up. One of our favorite things to do here is we look at customer tasks and primarily industry focus, and we slow down the videos and we watch the hands. And even the simplest pick and place, we're noting these complex in-hand manipulations, manipulating multiple parts at the same time, all of these things that just make no sense for automation to do, but it's giving them a speed advantage, 20, 30, 40% faster. So, the advantage of these human-like hands is it's certainly the most general purpose and capable end effector that we're aware of. The disadvantages are incredibly difficult to build, like cost and reliability are serious issues. And we're working through trying to get these. But very critical for in-hand manipulation. We do ablation studies on humans because it's much easier to like splint away a finger so you can't use it than to add it to a robot. And even with 4 fingers, your ability to do in-hand manipulation drops tremendously, and at 3 fingers, it's gone. And these are complex things, and we also have to consider the power too. So how do we get delicate and have this amazing dexterity? Like the shadow hand, I'm sure everyone's seen, is an amazing, phenomenal, dexterous hand. But how do we get the power too? And these are very difficult problems to solve, but exciting ones too.
Thank you. Alberto, in your view, what are the most important research challenges in dexterity? So how should we be investing our research effort in dexterous manipulation? Or perhaps more specifically, what results or technologies would you hope to see coming out of the hand ERC?
I think that so my read on sort of the state of the art today on dexterous manipulation is not far from what I presented on my slides. That there's 2 parts of the community that are betting on either large-scale simulation as the source of data and simulation, and part of the community that is betting on teleoperation for a source of ground truth data that is more appropriately embodied, not just in the form factor of the robot, but also on the perception that the robot is meant to experience, right? Like tactile sensing is very difficult to simulate accurately. And I think that we've seen enough today to understand that there is a lot of value on both fronts. It's difficult for reinforcement learning to parse through very complex long-term sequences of complex behaviors without some guidance, which could come from demonstrations. And it's also complex for teleoperation systems to do certain tasks that are just very haptic and require providing the teleoperator a degree of awareness of that hapticness that is still challenging today. So I was very excited to see Jeremy's videos today. I think that that's definitely an important direction. I would say that, in my view, the types of tasks that have more uncertainty today and less ideas for how we're going to solve, and it's probably a large fraction of tasks that we have to, are tasks that, on one hand, are difficult to simulate and also difficult to teleoperate, right? Like you're threading a bolt, and how do you make sure that the robot experiences what it means to cross-thread the bolt? I'm not sure that we're going to be able to accurately get that model from simulation. But I'm also not clear how someone through a teleoperated interface clearly understands that a bolt has been cross-threaded so that it can learn to avoid it. And just like that, I think that there's many tasks that fall in that category, where there's no clear idea for how we're going to solve them.
Thank you, Alberto. We actually have an audience question that I think you touched upon a lot of the points that were raised in it. So I'm going to speak it right here in case any of the other panelists have anything to add. So how important is tactile or force feedback, including in training by teleoperation? Do current robot platforms provide rich enough force and tactile feedback to train large models? Can this type of training be done in simulation?
Those are great questions. And I think most of us would agree that tactile is very critical. The way I've been viewing this problem for a while is that vision is very much a planning sense. You see everything in your environment. There's a cup over there and it needs to be in the dishwasher, and the rag over here and I need to wipe down the counters, or there's the broom and sweep it and put it in the trash can over there. And it's really critical to understand that if you had perfect information about your environment, you knew where everything was, you knew all of its properties, you don't need any sensing. You would just execute completely. And touch plays a very critical role for adapting on the fly for when things aren't as expected. You make a plan, something's off, an object slips, it's heavier than you think it is. Touch is absolutely essential for speeding this up, because if you don't have that critical sense, your only other option when something goes wrong is to step back, reassess, and make a new plan, which slows you down. So really the theme that we keep getting at is it's just about speed. Like all these 5 fingers, all this touch, all it is about going faster. The challenge with touch, though, is the durability has been a difficult problem. There's been, I haven't counted them up, but probably thousands of sensors from different research groups over the last decades. We've been really focused on durability and compliance, compliance is a very critical aspect that I think it's overlooked in touch, that we discovered at SynTouch long ago. Not only does it help with the durability aspect, but it gives you that wiggle room to react. If you have a rigid sensor and it collides with a rigid object, the forces go up rapidly. But if you have a compliance sensor interacting with an environment, you've got some wiggle room to respond to that collision before the forces go up high. It allows you to collide faster and produce lower forces and still be delicate. We could sense forces in actuators, it works. But because of the way the compliance and the inertia of the object is, you just have to move slower. So such sensing touch with the compliance sensors at the tip allows you to react and, again, speed everything up. So that's really the focus of what we've been thinking.
Thank you. Next, we have a question from Harsha Prahlad, who's a research project manager at Meta. And Harsha is asking, what household tasks cannot be done with today's state-of-the-art hands, and why?
Well, so I think, I mean, first of all, to add to the previous question, we do have, and many of them have not been publicized, but a crop of tactile sensors that are coming up, that they are new generation, much more robust, cleaner signals, and that's gonna be a game changer, because you really have to go sometimes to the hardware level, to the noise levels of your signal, whether the amplification and so on. And so the clean data is very important for training your processes. If you do it in the real hardware, and if you do it in simulation, we're also seeing a lot of trends of fast finite element method simulations. They can simulate soft interactions, and that's gonna definitely give a quantum leap to our current capabilities of manipulation. I think the areas that we cannot do are just immense, right? From tasks that require high stiffness and compliant control simultaneously, to high precision tasks, insertions, and dealing with hard and soft objects at the same time. And the viscous task, and I recall Alberto seeing tremendous advancements on sliding and dealing with the lack of models of what you are touching, and the ability of doing predictions or training for these unknowns. There is a vast variety of things unattainable at this moment. Meta is, I'm really impressed with their vision, and perhaps the area is maybe the home area, the home companion, things of the sort. I still like the idea of humanoids for everyone, in particular for families that are struggling, and cleaning. We saw how much effort it takes cleaning, and I don't think that this is a solved problem. Not only all the constraints, but having sort of these rich impedance behaviors of applying just the right scrubbing forces, and all of those are unachievable right now. And maybe, sorry, and just to make a last comment is that I would love to see out of this 10-year C, if you ask me, to see a taxonomy, expand the taxonomy that we have, the Katkowski taxonomies and so on, but also add new areas in terms of the complexity. Going to the Moravec paradox, why pushing a button is easy, but then scrubbing a hard to remove stain is difficult, right? What makes it more difficult, right? And then defining this taxonomy based on complexity. That's, I would like to see it as a hand ERC outcome. Thank you.
If great answer, Luis. If I can add one thing, there's something that I heard not too long ago, which I liked. I just want to try it here. So I think that one of the reasons why it's hard to answer that question of what are things that we cannot do at home today with current hands is that it's both a combination of what are the maximum capabilities of a piece of hardware, which are difficult to envision or to quantify, and our ability to exploit them, to reach that level of capability of what is the maximum that a certain gripper could do. And we're today still at a point where if we were to define a number, if that were to be possible, that is the fraction of how much can we achieve out of the total capabilities of a piece of hardware, this a particular gripper. That number is very different for, let's say, a parallel gripper that is extremely intuitive for people to think about, to teleoperate, to program, than, let's say, for a more complex gripper. Maybe that is not a humanoid hand or a perfect humanoid hand. So even though we have some degree of understanding of what are the limitations of parallel grippers, certainly two parallel grippers become a much more dexterous platform, maybe with the caveat, as Jeremy was saying, that you become less efficient because instead of doing this, you have to do this kind of thing, and it just takes way longer to do certain things. But in the path to get to hardware that is more capable, because it has more dexterity in that mechanical structure or more sensing, we still don't have a good workflow to exploit it. So if for a parallel gripper, we are at, let's say, 0.75% of what it can provide us, we might be at 0.25% of what another more complex gripper can provide. So I think that we just don't know how to answer that question yet.
Thanks for those thoughts, Alberto. That actually relates to another audience question that we had, which asks, in terms of mechanical design, what does the panel think about the role of inherent mechanical properties in the embodiment in achieving dexterity?
I would love to pitch, but I think Jeremy can start.
I think we're all going to agree that they're incredibly important. I think that the key thing here that comes with in-hand manipulation and other types of more complex manipulations is that dynamics come into play. So we're transitioning from quasi-static where, pick this up, move it over here, and if you change the velocity of that task, it doesn't matter. But as we start getting into dynamics, people are really good at dynamic manipulation. And I think that's one of the opportunities that these anthropomorphic hands bring to us. And with that regard, the mechanical design is essential. How do we get low mass fingers, strong fingers? These are the hard problems we solve. We want to cut weight, increase strength, increase power, add more DOFs. Like all of these things are in conflict with one another.
I just want to add that we still have a signature pending on the development, and I'm going to talk here about electric motors. I don't really have expertise with hydraulics. We can let Alberto talk about it. But electric motors, we do have a huge gap. First of all, here in the United States in particular, we hardly are producing competitive motors at the smallest scale for hands, providing something around 0.4 Newton meter on a PIP motor or something like that, which should be the target because that allows you the delicacy and the strength to lift something very heavy. So human hands can lift dumbbells pretty heavy, but they can also pick up a little screw and turn it in with the fingernails, right? So that those motor capabilities they need to happen, and I think there's activity ongoing on having an internal market. I hope in every country, but in the U.S. certainly that the market for small motors with these capabilities is small, and this is why we don't see players, but the technology is ready. And also gears, if you will, for quasi-direct drive in small motors with huge proprioception and a huge force and position bandwidth. Those are also areas that are ripe now for development. So we're going to see more of that taking place soon.
Thank you. Okay, keeping an eye on the clock, I'd like to ask just one final question, and I'd like each of the panelists to please spend 1 minute answering it. I'd like to hear from each of you. And the question I have is, what are you most excited about in this domain of dexterity for humanoids? If you're thinking,
Who wants to go first?
I can call on people too.
All right. Yeah.
I can go first. I would say my reason to get into hands, it's still the same as when I started my PhD with Matt Mason. Like I like crafting, right? And I spend most of my weekends doing things in my basement. It doesn't matter with cardboard, with clay, with wood, whatever it is. And I still feel kind of the same as when I started my PhD, that sort of our path to get these robots to do almost anything that I do during those weekends, it doesn't exist yet. It's still kind of hopeless. So I believe that there's something that we're missing, or there's something that we haven't unlocked yet. Because it's clearly possible we do it. And the range of tasks that are just extremely difficult to observe with your eyes, that you have no conscious understanding of what you're doing, but nevertheless you are doing them, is like extremely pervasive in our lives. And I'm just very excited. I think we are, in our lifetime, we have the possibility of uncovering that. And I'm just very excited for that.
Thank you. Luis or Jeremy, who'd like to go next?
Jeremy?
Sure. I think one of the things that I find incredibly exciting is really understanding this relationship between all these advanced capabilities of the human hand and how that relates to performance, and reconciling that with our customer use cases. I mean, it'd be great to build a perfectly human-like hand, but that's also incredibly difficult to do. So how do we meet where the technology is and where it can go and the customer needs? And this is a really exciting problem because, do we need faster hands, stronger hands, tactile sensing everywhere? which is something we are actually focusing on. But connecting the dots between how does hand strength relate to performance in very complex tasks is a very exciting research problem. It's something we're focused on working through with our customers and scientists together.
Yeah, I'll add my bit. So we LLMs are terrific. They are slow in terms of I'm a real-time systems person. For me, things are connected to a sensor modality and respond really fast. And exploring the verbal interactions with hands, with arms and hands, the very quick response loops, I think is very nice. Imagine the case where where a hand is helping to do physical therapy. So it's grabbing your wrist, and then you say something like stop, or oh, this is uncomfortable, move a little bit to the right, to the left, right? You cannot wait for going to a kind of a slow processing interface and kind of reason about the entire information and go back to the execution layer. We want to connect words to execution at very high rate. So when you say stop, it stops right away. When you say move to the right, in 100 milliseconds is doing that. I want to call it high bandwidth visual language action models, something like that, but deeply connected to the hand. So the hands respond to us the same as if a friend of yours is doing something with you, a collaborative task, and you say move here, move there, and then that you cannot wait, right? It's instantaneous.
Thank you. So I'd like to thank our panelists for sharing with us all your expertise and insights. It's been a fascinating hour, and I now will hand things back to Kevin.
Thanks, Brenna, Luis, Jeremy, and Alberto. That really was a fascinating discussion. And thanks to all of our participants online. There's so many excellent questions in the Q&A, and I'm sorry we did not have time to get to all of them. But we have recorded this webinar, and we'll make the link available soon. Also, shortly, you'll receive a survey, and we would appreciate it if you would share your thoughts on this webinar and possible future events that the HAND ERC can hold. For those of you who will be attending ICRA in Atlanta, please join us on May 19, where we will continue this discussion on robot dexterity at our full-day workshop, Handy Moves. We'll have some excellent researchers there and companies presenting their latest work, and I hope to see you there. Thanks again, everybody.
Thank you, Team HAND ERC.
Thank you so
Thank
much.
you.